share a lot of the details on how some of the results were actually produced in the previous talk. Before I start, everyone have a happy International Workers' Day. Important thing to get past. So as before in the talk with slides, I'm going to be first introduce the type of models we're working with. So we have a frame of reference. These are the spherical spin glasses. Spherical spin glasses. And these models are spherical because their configuration space is the n-sphere. So we have points x, which come from a configuration space, omega, defined by the property that x transpose x equals n. So really, it's not the unit n-sphere, it's the n-sphere with radius square root of n, which is a choice that is arbitrary and made so that everything in the mean field scales nicely with n in the end without having to do too much work. And the model can be thought of as being defined, as I said in the previous talk, by the covariance between 2 points in the configuration space. So if I have a nice sphere, I can't do the fancy dashes. I'll have to practice this part. A point in configuration space is a vector on the sphere, x. And another point in configuration space is also a vector on the sphere. And you can think of the model as being defined by a set of random functions, h, random Hamiltonians, say, who are Gaussians, Gaussian disordered, distributed at any given x, and whose covariance at two different x's averaged over the random functions is equal to n, again for scaling properties, times some function of the scalar product or overlap between the two vectors. Now it helps to make explicit an example, which are the so-called pure p-spin models, where f, let's see, I'm going to put it up here. Here, f of q, the overlap, is just 1/2 q to the pth power. It's a homogeneous polynomial in P. And a set of functions which create a model with this covariance would be functions h of x equal to the contraction p times of a p tensor with the indices I1 through IP with the vector x, I1 through IP, where the elements of this tensor are taken to be IID Gaussians. So if you have a model of this property, you take the elements of the tensor to be centered IID Gaussians with a variance that's properly chosen with the right factors of n, not that important conceptually. You'll find that if you compute the covariance at two different points, you have something exactly of this form where when the interaction is a simple p tensor, you have a covariance with q to the p, the overlap to the pth power. Nathan has a question. So J is Gaussian distribute. No, they're at each, if I'm doing a simulation of this in the computer, I want to make a function h of x that I can, do gradient descent on. I come up with n to the pth power j's by pulling from a normal distribution, C++ standard normal, and I fill this big tensor with random numbers from the normal distribution, and now I have my function by taking that big tensor and dotting it into the positions on the sphere. It's not a function of anything. They're random numbers, and each h has different set of random numbers j.
Range over everything from -infinity to infinity?
They're normally distributed. So they could, but it's very unlikely that you get very past the variance.
So we're focused at 0, is that right?
Yes, these are centered.
Okay, good, great.
Yeah,
Okay,
exactly. Sorry, the covariance is given by F. Yeah, so in fact, the variance will be given by, yeah, the variance of J will be given by F, exactly. I mean, in fact, here, it's not really given by F, because you can see, in this direction, we've said, okay, the F is just 1/2 Q to the P. So the variance of these J's ends up being something like a factor of 2, a factor of 1 over n to the P minus 1 so that our energy is extensive. And I think a factor of P factorial because we have too many contractions on a symmetric, something that should be symmetric, in fact, in this case.
So what sense is the spin model? Does X are spins?
It's a bit of a strange thing to call this as a spin model. I mean, it's called a spin glass because it operationally is very much like a spin glass in terms of the way that we study it and the kind of abstractness of the model. But yeah, you can think of the x's as, each component of the x is a spin, and there's a very strange constraint on the values the spins can take. I find it more interesting to think of this as a model of a single point on the high-dimensional sphere, and then that's the model. And what we're studying are, in this sense, not spin glasses of like, okay, we're imagining some sort of material with little spins inside it. And rather, we're studying properties of generic random Gaussian functions on the sphere.
So in terms of a model with matter fields, what would this correspond to? In terms of, the models that you're talking about, spins, what does it correspond to?
What does it correspond to?
Right. Do you have a material with this property? What kind of system do you want to describe?
So right now, I really just want to describe properties of generic random functions. And the question then would be, what systems have behavior which is like that of generic random functions? And the answer is, okay, perhaps some spin glasses. Okay, maybe we can have an inference that's qualitative, the way that mean field theory usually informs finite dimensional behavior. But also, these actually very closely resemble a certain model known as the spiked tensor model in statistical inference, where you imagine that you want to find a certain vector that's been normalized, so it's on the sphere, and all the information you have about that vector is a low-rank tensor built from the vector. So you have some tensor, xi1, xip, from some, let's say, x star, some special vector on the sphere. And this is what, you want to find out what x star is, the vector. The information is this tensor, but it's also been corrupted by some noise, some random noise that's, normally distributed. Now, in this problem, if you write down the least likelihood sum of squares cost function for finding the most likely x star given a set of data like this, you in fact get something that looks exactly like this, plus external field in the x star direction.
Sorry, Jaron, this is, as we all know, is just a generalization of the Sherrington-Kirkpatrick model, correct?
It's a different configuration space, and the Sherrington-Kirkpatrick is on the... Sorry?
It's on spins. The Sherrington-Kirkpatrick is spins where they all interact with each other equally.
Yes.
The strength, which is random, like the one you have there, divided by root n or something to have a finite limit, okay?
I mean, I agree, yes. The Sherrington-Kirkpatrick model is very similar. It's more...
It's the origin. Not only similar, it's where all of this started.
Well, the configuration space changes a lot, for instance. I mean, there's been a lot of work recently generalizing certain kinds of fancy message passing algorithms for finding low-lying states in these systems. And you can write down these algorithms both for Ising spins as your configuration space, so on the hypercube, or you can be on the hypersphere. And what you have to do to find low-lying states changes in qualitative ways.
So you mean is the ON generalization of the Sherrington-Kirkpatrick model? Is that what you have in mind?
It's very similar, I agree. It's very similar. There's very different behavioral properties, but you're right, it's random couplings between the states of some elements of configuration space.
Sorry, but in the Sherrington-Kirkpatrick, the possible values of the xi are just 1 and minus 1, right? Here
Precisely
instead,
yes.
Here they are continuous.
Yes.
Okay.
Yes, on the ON model, they are continuous. there is a spherical mode that people write.
Exactly. So I
Yes,
would say
yes.
this is
The
the main
larger
difference,
limit.
no?
It's a large, there are two ends in that case. It's the end of the number of spins and the end of the rank and all that.
Another question, is it possible that the p-spin, like the spin behavior becomes more evident if you quantize the model?
I really shouldn't have written spin because it's
Okay.
completely besides the point of this talk.
Okay, fine.
The types
let's
of
skip it.
systems that we really hope to describe with models. So why these models were found interesting in the first place was not because they were thought to describe material spins. It's because when you write down the dynamical mean field theory equations for these models, they have the schematic form of the same equations you find in the mode coupling theory of structural glasses, not spin glasses.
I see.
And so the motivation for these models is very far from trying to describe systems of interacting spins. It's to describe things that we think will be described by continuous random functions. And
Okay,
the closest examples to the things of these models are systems like structural glasses in a very schematic kind of qualitative way, and in certain kinds of inference models where actually there are very close connections.
And also, this is really a curiosity
Yeah.
related. I mean, the reason why people take Gaussian things is always because there is central limit theorem. So, but there is an exception: the various Levy distributions. Is
Yes,
there
yes.
anything known about the behavior of the model when you replace the Gaussian with some Levy fat tails distributions?
I don't know of any work on this,
Okay.
but I imagine people have thought about it.
Okay.
I mean, at the end of this talk, I'll be talking about what I'm going to call non-Gaussian landscapes, which are a little bit of a confusing way to pose it. So this is a Gaussian landscape because literally the value of the function at different points is Gaussian distributed. The generalizations I'll talk about will still have a disorder generated from a normal distribution, but the values of the function will no longer be normally distributed because the disorder will enter the function in a nonlinear way.
I see.
Jaron,
Just a comment. No, just two comments. One is, Dario, I can send you some references about Levy-like interactions later if you wish. I can send you by
Okay,
email.
yeah, sure,
And
thanks.
the other comment is that, Eduardo, the model like this is more similar to the CATS spherical model than to the ON.
Yeah,
But they
that's
are
what I meant.
very, very similar indeed,
Yeah.
both of them
It's a
anyhow.
large end limit of ON.
Exactly. Yeah.
I understand that. Now, Jaron, you mentioned structural glasses. And I never understood the connection because structural glasses are not disordered systems.
Indeed.
Are frustrated systems, but they are not disordered. There is no randomness in structural glasses.
The connection is very explicit. It's that when you write down the mode coupling theory equations for structural glasses, and you write down the dynamical mean field theory equations for these systems, they have the exact schematic form.
But where does the disorder come from? Those are not disordered systems.
I wasn't involved in this stuff because it was done like 30 years ago, but the basic motivation for why these would have the same schematic form is that in these simple p-spin models, the pure ones, the form of low temperature order is a fracturing of the phase space into tiny disconnected components, which is the picture of the random first order transition of glasses. And so the idea is that this schematic type of order you see, even though it comes from a different source here, the disorder in this model and whatever strange properties of the non-disordered energy function in structural glasses, the type of order on the underlying model should thought to be similar. Again, this is quite controversial in even modern research. I don't want to get into that argument because I don't really have a strong opinion on the matter.
Okay, so fine. You take. I understand. You take. In the U.S., it's called. You take the Fifth Amendment. You don't want to.
Yeah. Yeah.
All right, go on. Sorry.
I mean, I think one should be able to have a lecture about spinodals without a big argument about whether they exist in 3 dimensions, for instance.
Yeah. Okay. Fair enough.
I just had an easy question to answer. So it looks like H. It's on. H of x looks like it goes like square root of n to the p, right?
Sorry?
H of x looks like it goes like square root of n to the p.
If you base it on the x's themselves, but I told you that in the variance of the j's, you insert some factors of n to make sure that it has the correct scaling.
Okay, thanks.
It's really conceptually unimportant, but I could write it down if you really like. All right. So our goal with models like these is to describe the number of stationary points, minima, maxima, saddle points with certain properties, for a typical one of these functions. You draw one from the distribution, it'll have some number of stationary points. We want to know how many it is likely to have. And in the large n limit is where we'll be working. So I should define the quantity we compute to answer this question of the typical number of stationary points with certain properties. And this is the complexity. In this field, that's what we call the number, complexity, which is defined by, it's going to be this sigma, defined by 1 over n, so normalized to be a intensive value, times the logarithm of the number of stationary points averaged over the disorder. Now this implies, right, that the number of stationary points will tend to be e to the n times the complexity, so exponentially large in the size of the configuration space within a amount which is given by the complexity. So the complexity means 0 means that we expect to find order 1 or fewer stationary points, or let's say less than order n. If it's negative, okay, vanishingly likely that we find any stationary points with properties of that type. Now,
should it obey positivity conditions?
Sorry?
This sounds more. Should it obey positivity conditions? This sounds like entropy to me, which are defining.
Sorry,
here.
I can't hear what you're saying very clearly.
Should it be? Is there a positivity condition?
Is there a
This
positive?
sounds like it sounds like an entropy, which are defining.
Yes, it's a lot like an entropy. I mean,
Yes.
there's a sense in which the complexity can be negative. It's okay. It's not actually a contradiction. What it's telling you is that the expectation value for a given sample to have a stationary point with the properties that you specified is something which scales very poorly as n gets large. So it's vanishingly unlikely that you find something with those properties.
You mean that this may actually have a distribution with tails that?
Oh yeah,
will go
it certainly does. I mean, you can construct all kinds of very unlikely tensors J for which a stationary point with arbitrarily high energy exists, but the likelihood that you actually find this when you sample the distribution becomes extremely, extremely small as n gets large.
So in that sense, it's not really an entropy. Okay.
Perhaps.
Okay.
So I'm going to do a lot of manipulations soon with this expression to actually show you schematically how it's computed in these models. But the very first and important manipulation is to deal with this logarithm, which is a big pain, because I'm going to be able, through a few tricks, basically, to write this curly n as an integral over configuration space of exponentials of various parameters, very much like a nice field theory. But the logarithm is trouble because I can average over the exponential integral, but I can't average over the logarithm of an exponential integral. And so we're going to incorporate the classic replica trick, which is based in its first writing down on an identity, a trivial identity, which is that if I take the limit of a real number n to 0 from above of the derivative of something to the nth power, this is just the logarithm. This is, a nice high school math problem. But the crux of the method will be to pretend, looking at this expression here, this curly n to the nth power, that in fact you're looking at a nice integer number of, integer power of our number of stationary points. And that, therefore, rather than deal with some continuous variable, we can look at the nth moment, right, of this distribution of numbers of stationary points, compute it, again, the whole time dealing with integers, and then forget about the integer part, take the limit of n to 0, and be satisfied with our results, which is mathematically somewhat fishy, but in almost every example to date appears to work, much to the chagrin of the mathematicians. who have to come up with much more fancy methods to get around this.
Perhaps, I mean, you know, the replica symmetry is always, the replica, let's say, the replica trick is always a bit controversial and so on. Does exist? Can you use the supersymmetric method for these models or not?
Yes, in fact, I'll describe the supersymmetric methods
I see.
later in the talk. It's an
Okay.
important part of actually getting answers out of this system.
Mhm.
So this is nice. So later, the fact that we did this will help us actually make averages over this order. But in the meantime, we also have to deal with the fact that this curly n holds a lot of promises. I told you it's the number of stationary points. It's not trivial to imagine finding the number of stationary points. So how do we actually get curly n? For that, I'm going to go to a faraway board where I can store my formulas. Let's see how this works. Yeah, I'm still on screen. So I'm going to write down curly n using a kind of funny, let's say, stupid schematic form to start with. And that is, I'm going to imagine I already know all of the stationary points, right? I'm going to say curly n is just equal to the sum over all points such that the gradient evaluated at the point is 0. That's just the definition of a stationary point, of 1. This will give me the number of stationary points. It's quite clear. Now, the thing that we do to then bring that into a computable form is to play a little bit with the neighborhood of the stationary points. So if I come back to my nice sphere on this side, so if this x is a stationary point, it has no gradient in the direction it's pointed, right? The gradient's 0. But for points close by, some x prime in the near vicinity, the gradient will be some other vector. It'll be a non-zero vector. And because these are generic functions, right, we'll never have a nodal line of stationary points. That's vanishingly unlikely. It's literally a set of measures 0 in the space of these functions. And so, in fact, there's in a sufficiently close neighborhood of our stationary point of interest, there's a one-to-one mapping between nearby points and vectors in the tangent space to the stationary point at x. So we can make a one-to-one mapping between, literally, points nearby and the gradient vectors associated with points nearby, again, in a sufficiently small neighborhood with respect to x, right? So this means that we can go, well, first, what it means is I'm going to write down another kind of stupid form here. I'm going to keep this sum over x such that the gradient is 0 of now something which equals 1, an integral over the tangent space of the manifold evaluated at the stationary points, each one, times, this is going to be kind of silly, but you'll have to bear with me, the integral over gradients, treating it as a dependent variable, by the delta function of the gradient. This evaluates to 1 at each stationary point. And once again, we have the count. Yes?
So I understand correctly that you made an assumption that you don't have flat directions because you don't have the degenerate minima?
We don't have exactly 0 flat directions, yes.
So you don't have the degenerate minima continuously?
Exactly. It's a set of measures 0 when you draw points from this function.
And if you had, what would change in this integral?
Whew, there's a whole field of people who try to extend Morse theory to non-small functions, but I am not an expert in that field because I like to work with random functions, which, again, it's vanishingly unlikely you find these properties. But I mean, people study this. I'm just not familiar necessarily with.
Okay.
A lot has to change, clearly, because, I mean, continuous lines of stationary points is a problem when we want to make a number, right? Now we have a volume of stationary points, something like this.
Okay. Thanks.
I'm a bit confused because in the previous talk, I mean, there were many valleys with, so here, this is orthogonal to all that situations.
No, I mean, I talked a lot at the previous talk about marginal minima, which have asymptotically flat directions. Flat for all order n is concerned.
Repeat, flat?
So the directions that are flat for all order n is concerned. But it's actually, again, vanishingly unlikely that any eigenvalue is exactly 0.
Ah, I see. So here you accept that, let's say, gradient of h is very small, that is fine, but not 0. That is really...
Well, it'll be 0 at the stationary points, but yeah, in some direction out, you can have a curvature which is extremely small.
Okay,
But
fine.
Again, you have to do fine-tuning of the tensor of interactions to actually find an example of a function which has an exactly nodal line coming out of a stationary
I see.
point.
Okay.
So now the trick is going to be to exploit the fact that we can do this mapping from nearby points to the gradient. And that is going to be to change variables in the integral from the gradient to the points, the configuration space. And that is where we get the form that we like. So now we're going to have an integral over the configuration space, now of the configurations, at the cost of the Jacobian, the determinant of the Jacobian associated with this transformation, which is going to be given by the absolute value of the determinant of the Jacobian, of the derivative. I'm going to write a lot of these partials with no arguments. That's always partial with respect to x. Of the gradient, multiplied now by the gradient of the delta function of the gradient evaluated at the configuration, where the sum is now absorbed into the delta function. And this derivative of gradient up to rank 1 corrections, which are not relevant at large n limits, but you would have to think about if you wanted to get subordering corrections, is just the Hessian of the model evaluated at the point x. So this is the so-called Katz-Rice formula. It's also schematically the same as the so-called Fadeev-Popov gauge fixing method, where instead of the gradient of h being 0, you would use your gauge fixing condition should be set in the delta function, and you have this determinant involving the derivatives of it. But an important difference that you don't think about at all in the Fadeev-Popov usually is that there's these absolute value signs on the determinant. And these turn out to be very crucial in our case. They tend to be thrown away without thinking in the Fadeev-Popov case because you typically expect to evaluate your gauge on one point of the the gauge invariant Lie group, let's say. And so you have something which, over the integral adds constructively. So the fact that you threw away the sign of the determinant, it's not that very important. Whereas here, the sign of the determinant of the Hessian is given by -1 to the index of the stationary point times, the determinant of the Hessian, right? It's the product of our eigenvalues. If we have the index of a stationary point is the number of downward directions, the number of negative eigenvalues, so we get -1 to the index times just the value without absolute value signs. And in this case, so I wrote this formula down with no other conditions, just the total number of stationary points of the function. If I tried to compute that, having made the simplification, the nice one, because of course once I drop absolute value signs, a determinant of a matrix could be turned into a nice integral over Grassmann variables of an exponential form, which is exactly what we like when we're doing all kinds of field theory, mean field or not. With the absolute value sign, this isn't possible. But if we drop it, we try to take the easy route, use nice Grassmann variables to describe the determinant, we find something funny, which is you can imagine dropping this and trying to go backwards through the derivation I would give. You would get, in this second step, the sum now over indices of the number of stationary points that have that index times -1 to the index. You're just now summing in a non-constructive way the numbers at each index. And this, from more small theory, gives every time the Euler characteristic of the manifold, independent of the model, independent of our function. And so if we want to learn something about the structure of random functions, we really shouldn't compute this, because it's completely invariant to what choice we make about correlations among the points in the random function. And so this absolute value sign, it turns out to be quite crucial. And at the end of my talk, I'm going to be discussing, as I mentioned, some challenges, where in this derivation there are challenges in non-Gaussian landscapes for which the disorder, I mean, the simplest cases, the disorder enters the energy function in a non-linear way, and they're all basically going to be concerned with how to deal with this.
Sorry, what is the dimension of this Hessian?
Sorry?
What is the dimension of the Hessian of age?
It's going to be n-1 by n-1 in a strict sense, because it exists, it should be the matrix of the Hessian in the tangent plane to the stationary point. I am about to forget about manifolds for going forward and use a Lagrange multiplier to treat the fact that we're on a surface. And then it will simply be an n by n matrix whose behavior coming out of the plane, again, being rank 1 in a large N problem, will be not relevant to the description of the problem at the highest N limit. But I mean, it's true, if you want to make higher N corrections to these calculations, you have to very carefully monitor the fact that you actually have an n-1, n-1 Hessian. This outward direction is not physical, and you treat everything very carefully. Here we'll just use the Lagrange multiplier and rely on the fact that small perturbations are not going to change the answer.
Sorry, just to be sure that I'm still following.
Yes.
I mean, you say the summation over the zero gradient point and so on,
Yeah.
if I understand correctly, is interesting exactly because of that -1 to the index that prevent the answer to be a topological stuff, right?
Yeah, precisely.
Okay, got it. Okay.
Yeah. Again, this is also the case where I have not made any conditioning on interesting properties like the energy or something.
Okay.
One of the ways out of this pickle is to condition your problem on energy or index of the saddle point in a way which means that the overwhelming majority of the things in the sum add constructively. This is a way out that you can now reliably make calculations neglecting the absolute value sign. But in general, you have to think critically about whether you drop it or how you deal with it.
And in that formula, because that formula, the last one, not the last one, sorry, the one in which you integrate over omega, seems to be, let's say, operationally useful, almost, but you still have the delta function. So you are going to exponentiate the delta function.
Precisely
and,
this, yes. I'll introduce lots of delta functions, all of which we'll treat by the Fourier representation.
Okay.
And resort to, and we'll have a nice theory, which is an integral over exponential things that have linear dependence on these J's, these are H's.
So there is an old problem that was studied by Parisi and Surlas, the random field Ising model, where they notoriously drop the absolute value.
Well, so in that model, it's quite, so in the random field Ising model, the way that this is very technical for people who aren't into this, but the way that you derive the effective theory they use, which has a emergent supersymmetry, is not from a calculation of this kind. It's from a very similar calculation using the dynamics. You insert the Langevin dynamics for the model into a delta function, like you do in DMFT, and then you carry out the steps. But in DMFT, each initial condition and instantiating of the disorder only results in one trajectory. And so in fact, the determinant in a lot of ways contributes trivially, or contributes once for every possible instantiation of the dynamics. And so its influence on what happens in the calculation, it's qualitatively different, because like the Fadeev-Popov case, it only really gets hit one time per...
Yeah, but the case failed precisely because of the absolute value.
That's not true, actually. So the failure of the supersymmetry in the Sorlas-Parisi case is because writing down the equations for the mean field equations for the random field Ising model as this effective Langevin dynamics already contains an assumption about basically tree-likeness in the diagrammatic expansion. So it's before, the step before actually writing down the dynamical equations where there's an assumption that's made, which is...
This is not related to Griffith singularities.
Sorry?
I thought it was the problem that with the absolute value there are Griffith singularities, which were essentially neglected by them in the partition function. It's not dynamic. It's not equilibrium.
I had a lesson
So
on
what-
this by Slava Rykov recently, and so I
Yeah.
have his explanation in my head, but it's possible people have tried to explain it with other ways too.
Well, this was the original problem because they predicted famously dimensional reduction, which doesn't exist.
Yeah, yeah. I think it's
Uh,
much better understood now that the supersymmetry really emerges when you can neglect diagrams in the field theory beyond tree level. And it's precisely these loopy diagrams which, when they become relevant, ruin the supersymmetric answer. This is, again,
see.
Slava's story when, he's been looking for very complicated relevant operators that change relevancy around 5 dimensions in order to try to explain this quantitatively.
No, unit singularities are more serious. These are essential singularities in a partition function.
Okay.
So I thought that this was, in fact, the original derivation did not involve dynamics. It has nothing to do with Langevin. It was all done with partition functions in equilibrium. Okay, so well, okay.
But I think
Okay.
that the understanding of Richthof and his collaborators now is along the lines that Jaron was saying. I mean, it's not great singularities. It's much simpler. It's just perturbation theory and graphs that you have to take into account, and that ruin things in low dimensions. Yeah,
Okay, so this is unrelated to this absolute value problem here. Is that
I think
okay?
so. Yeah. Yeah.
Okay.
There's at least
Sorry.
another problem in the supersymmetric.
Yeah.
Okay, whenever I see absolute values, I remember Parisi-Sourlas. Okay.
All right. So back to this model, I said that we are going to dispense a little bit with trying to think rigorously about manifolds, which is a little bit of baggage to carry, and move to a Lagrange multiplier description. So basically, we're going to say a stationary point. We'll introduce a Lagrangian rather than just the function, where the Lagrangian is just the function plus something to keep the spherical condition, which I use sine and 1/2 conventions. My Lagrange multiplier I'm going to call little omega times the constraint that we stay on the n sphere.
Mm-hmm.
And this immediately spits out what we should put for the gradient and the Hessian, basically correcting for these outward directions we don't like, which is that the gradient of h should be the derivative with respect to x of the function, the simple derivative, plus omega x. And the Hessian, likewise, of h of x should be the double derivative. This is a matrix derivative of h with respect to x, plus an identity multiplied by the Lagrange multiplier. So this is going to, involving this Lagrange multiplier, fix our outward direction problems that we don't care about because we're on the manifold. And this leads us then to write down the number of stationary points, right, in a full glorious form. So we have n is equal to, as I said, an integral now over just all real x because we're using a Lagrange multiplier of dx, d omega. We have to integrate with the Lagrange multiplier. Our constraint that comes from taking the derivative with respect to the Lagrange multiplier. All of this stuff, the delta function of the derivative of h at x plus omega x, that's our gradient, times the absolute value of the determinant of the Hessian evaluated. Oh, sorry. I'm not going to write the Hessian. I'm going to write this form that I just made up from the Lagrange multiplier, the double derivative of h in a matrix form plus omega I. And now I'm also going to add 2 other delta functions, like you saw.
I'm just a bit confused. So
Yeah.
you define a new Hamiltonian with the Lagrange.
Well, you're in a Lagrangian here. Yes.
A new Lagrange. Oh, sorry, I'm confused. So this is a Lagrangian now.
So Lagrangian in the numerical optimization sense, not in the field theoretical sense, but if you know, Lagrange multipliers, you write down a Lagrangian for your constrained optimization problem by adding a Lagrange multiplier. And the value of the Lagrange multiplier evaluated at our stationary points will basically do the trick of subtracting out the outward or inward direction of the gradient so that, you know, a point that has all 0 directions except for out of the sphere, that we should throw this away. We should consider this a stationary point, right? And this will accomplish exactly throwing out that outward direction by tuning the Lagrange multiplier to the right correct value at each stationary point.
I guess I'm just confused by notation. That's okay.
It's a Lagrange multiplier, not a Lagrangian. Okay.
That's what I thought. But this is a new, what he wrote there, H plus this Lagrange multiplier.
He's softening the constraint. That's all he's doing.
You can consider it like this. You could also do the exact same thing by just making a soft constraint where you have some sort of potential that holds you on the sphere, that you take the limit of the stiffness to infinity at the end. It does the exact same thing.
No, I understand. It's just, okay, it's just notation. Okay.
Yeah, it's just notation. So I'm going to add 2 more features to this, which I really should have anticipated when I didn't give myself space here. Because in my talk on Monday, I emphasized it was interesting to look at stationary points with certain features. Right? This is the total number. It's an interesting thing to calculate, perhaps, if you want to know whether your problem will have lots of metastable states or, you know, just one solution. This, if you're doing numerical optimization, this is a useful thing to understand. But it's also interesting to know the properties of these things in slices of energy, and in, I described on Monday, stability, which basically accomplishes fixing the index. So we can add this dependence through more delta functions. Sorry, not more Lagrange multipliers. Don't worry, these are the only one of those. More delta functions. We can take one delta function, which fixes the energy, by saying, you know, n, the energy density to order n, minus the value of the function at a certain point, times, again, this funny thing, the stability I defined on Monday, n times mu minus the trace of the Hessian, which is going to be the trace of delta delta h, partial partial h, plus omega I. And now we have some knobs to turn in our count. We can specify properties that may be interesting to us. The height, and as I explained on Monday, this accomplishes, and I'll also explain a little bit when I describe the Hessian terms here, this accomplishes essentially fixing the type of stationary point, the index density to order n, or the stiffness of the minimum that we're talking about.
So effectively, by this last delta function, you can, in a sense, get rid of the absolute value, because the absolute value is there to count if they are -1 + 1. And,
not quite.
I see.
So when either of these conditions puts you into a regime where the exponentially dominant population are minima or maxima, then you can drop, because you will have 1, 1, 1 every time.
Exactly.
The problem is that in a regime where saddle points are most common, this is a calculation, and this is a delta function, which is only constraining things to order n. And so little fluctuations in the number of downward directions for the given saddle, you know, whether it's, you know, some plus or minus a few, this will happen, and of course, punish you all the same, right? Because the -1 is doesn't really care about your little, the fact that you're making little fluctuations, right? You'll still have an incoherent sum. And so if you're interested in characterizing saddle points, this doesn't work.
I see.
So just for me to understand, this is for for one realization.
One realization of this order. This depends, there's a little lower, I can put a little lowercase, a little h, uppercase h here to say that this count depends on h.
Okay, good, thanks.
Yes. And so we want, again, to make this calculation of the complexity, which means that we need to know the nth moment of this, this count, which again, I have very foolishly not given myself enough space. So I'll move over a little bit. This is going to be our count of E and mu, which depends on the specific instantation of the disorder, should be equal to now an integral over, sorry, to the nth power. We want n of them. This is our nth moment calculation. Over the product now of basically everything in here, n times. So we have some index a, which goes from 1 to n, and we have to put an a on everything throughout. A. This depends on x, so that gets an A, yes.
Think is diagonal in the replica?
Right now, before we take an average over disorder, it is exactly factorized over the replicas.
Okay.
But once we take the average over disorder, we will find that there's all kinds of mixing.
Okay, fine.
But for now, no, it's diagonal. Because it's just, again, it's just the integral we took to the nth power. We haven't taken any averages yet. And then the average is where the fun comes in. And so now if we want to take an average, we would just, okay, it's easy on the board. I just draw a line. I have to draw a line over everything, the whole integrand. Big long line. Schematically nice and simple. But now we have to actually deal with evaluating this. And as I said before, in principle, the fact that we have this absolute value of the determinant makes things a mess, right? Because what we're going to do with everything else is use the Fourier representation of the delta function, have exponentials with now ghost or auxiliary fields to come from the Fourier representation of the delta function, and then take averages, have order parameters, write down effective actions in exponential form. But this is a problem. Fortunately, it's not a problem for us because we're working with a Gaussian random landscape. And it's been shown that in Gaussian random landscapes, in the large n limit, the Hessian is an independent random variable, not the Hessian, sorry. The second derivative of their energy level with respect to the x is an independent random variable from the gradient and the energy itself. This was shown by Bray and Dean, like the mid-2000s, 2000-aughts, let's say. It's a very nice result. So what let's do is come to this form here.
I'm sorry.
And break this big long line into two pieces. One piece which only covers the parts that depend on the double derivative of h, and one piece which depends on everything else. So that second piece is only nice delta functions that we can use the Fourier representation on. The other piece we'll deal with ideas from random matrix theory, preserving faithfully the whole time the absolute value signs, which is not going to be difficult because being independent from the condition that we're at a stationary point, this will become basically the easiest random matrix theory problem that exists, which is to find the typical absolute value determinant of a shifted symmetric random matrix populated with Gaussian numbers, which belongs to the Gaussian orthogonal ensemble, which is a very simple, well-described ensemble of random matrices. And so with that, I'm going to work on that first term. I would have just broken the line in a beautiful place, like here. But then I foolishly put the other Hessian-dependent term on, not next to the first one.
Good question.
Yeah.
WA, you don't really want to integrate it because you've already pulled down the delta function, right?
Oh, we want to
Omega A.
integrate it. Oh, sorry, I missed a W. We do want to integrate it. We'll see that the effect of integrating it is very simple. In fact, in the part I'll just discuss about the term, the average over the term dependent on the Hessian, it'll turn out that the effect of integrating WAs is to set them all to mu.
No, I understand that WA is fixed because of the delta function of DH plus WAXA. That's going to fix WA.
It's not fixed. So for each stationary point, it is different, in fact,
Okay.
in principle.
Okay.
It basically, so think about this. The term that, if you have the derivative, not the gradient, of this random function at some place on the sphere.
This may be distracting, so I apologize, but you're doing a functional integral over the w's, right, in the x's. You have this.
Not a functional integral, a regular integral.
Yeah. Fine, but the delta function of xa minus n comes from that integral, right? Because you put it in the Lagrangian and you integrate it over w, that gives you that delta function.
Yes, indeed. Yes, I agree.
So you've already integrated over the W.
That's not true, right? To do this sort of, to evaluate a stationary point of this Lagrangian problem, I need to evaluate stationary, I mean, you're right, I've taken the derivative of this to produce the constraint, but I also have to treat it as a full dynamic variable in where it enters in the derivatives with respect to x.
Okay, let's talk about this later.
Okay,
I think this, okay.
Sure.
Go back to your thing. Okay, go ahead.
So let's talk about the Hessian terms. I'm going to move back to this board here. Okay. The Hessian terms. I guess factors would be more appropriate. So these contain this delta function of the trace plus, also, not plus, multiplied by this absolute value of the gradient. And we're going to evaluate these relying on the properties of this matrix, the double derivative of H, which, as I've said, it's a symmetric matrix because it's double derivative, and it's real valued, we have a real function, and its entries are Gaussian with some variance because they come from, evaluating this thing, evaluated at certain points. Which means it's going to lie in our double derivative of H matrix is going to lie in the Gaussian orthogonal ensemble, a very well understood, very well controlled matrix ensemble in the large n limit. Yeah, also H of x isn't a matrix. It's also a Gaussian, but it's not a matrix. So, I mean, in a sense, it's not a GOE. So this teaches us two things which will be very nice for us. One is that the trace of this thing, just the double derivative, not the Hessian, will be typically order root n. Smaller by an asymptotic amount than the contribution from the trace of the identity here in this delta function. So what effectively happens in the large n limits for this trace of this matrix is that it will drop out of our little computation, at least in this delta function. I concentrated all my erasers on one side, where they started over here so thoughtfully. So it'll go away, and the trace of an identity is n, so we just get omega a times n. As I promised, the effect of this delta function is to say I want to count stationary points. You can consider it like this. I want to count stationary points with a certain Lagrange multiplier. That's another way to say it. Or, again, I want to count stationary points with a certain projection of the derivative of h onto the perpendicular of the manifold. This is also the same. Yeah, because think about the Lagrange multiplier has to be subtracting out effectively that perpendicular direction, right? So we took the derivative of h plus omega x, and so in order for this to really be a stationary point in our picture, it had better be true that omega is minus the derivative of h dotted into x, I guess normalized by the norm of x squared. No? This is how you say, okay, now I have a vector in the tangent plane. This is just we could have actually, I've done this calculation in situations where this seemed fishy, using instead this to fix the constraint. So forget Lagrange multipliers, just require that you subtract out this projection, and it does exactly the same thing. It just is harder. Anyway, so that's the first thing that's happened. It's very convenient. The second thing that we learn is the asymptotic spectral density of this matrix. We know that the distribution of eigenvalues in the large n limit for the double derivative of h which I'm going to call rho of lambda, as a function of lambda, takes the form of the so-called Wigner semicircle, which is a huge misnomer because it's an ellipse. The two axes have different units. That is a decent circle. Not great, but it's a very nice ellipse. And all we need to know to specify the form of this spectral density is the variance of the entries of this matrix, which are given by, if we look at the, a certain ij squared of this matrix, a small calculation reveals that this variance is, let me think for a second, 1 over n, this is important to have the right scaling to be a Wigner matrix, times 1/2 times the double derivative of our covariance function evaluated at 1. Sorry, I'm missing a very important piece. Average over disorder. So this is the variance of our entries of our random matrix, which going through the, the machinery of well-established random matrix theory tells us that this width of this distribution will be derived directly from this. It turns out to be, I called it mu m in the previous talk. It's given by the square root of 4 times the double derivative evaluated at 1. It's some value directly dependent on the choice of covariance function I made. And that gives us the width of this semicircle. Yes?
Yeah, how does this absolute value business enter now? Because this actually is a symmetric density of states, has both positive and negative eigenvalues.
Yeah, we're about to get there. I'm going to derive the determinate absolute value in just a second.
Okay.
So this is telling us the spectral density, the distribution of eigenvalues asymptotically for this double derivative matrix. But we don't have that. We have double derivative matrix plus an identity scaled by our Lagrange multiplier. Or I could immediately just say, okay, now I integrate the Lagrange multipliers, It kills this delta function. It puts a mu everywhere that I saw one. Yeah. So that distribution is instead going to be this semicircle, which is centered, shifted, all the eigenvalues, added mu to them, right? That's what this identity will do. And so this, by the way, is how fixing this trace allows us to fix types of stationary points in these models, is that fixing the trace fixes the shift, right, of the distribution for the Hessian to different values, say only over positive support or, over negative support with some proportion of eigenvalues with negative directions. And this is why mu is a useful way to talk about types of stationary points in these models. Obviously, in more generic models, you don't have this promise at all, and you have to be more clever. But in these models,
So
it's very convenient.
mu is a parameter now, or mu is
Mu was always a
something
parameter. Mu was always fixed. It entered in a delta function we inserted here to be opposed with the omegas, which were active, dynamic variables in a sense in the Lagrange treatment of the optimization problem, if you will, the constraint optimization problem.
mu is like a chemical potential in the usual sense?
It's not. It's an unfortunate overlap, I would say. You only have so many letters.
So now my
No,
question.
no, it's not the question. It's conceptually like a chemical potential. You're fixing, so you're working at fixed mu. Mu was not part of the original problem in the sense.
It was not part of the original problem. Mu is actually more like fixing the number than fixing the chemical potential, right? If you want to fix the chemical potential in a sense, you would want to fix something which exponentially weights the index, right? So mu is more like you're fixing the index to a specific value. It's like the microcanonical version in a sense.
Okay.
Also fixing E, right? This is very microcanonical in this respect.
Okay,
My
thank you.
question I was going to ask at the end, I think I have to ask now. So, so suppose we didn't have mu.
Yeah.
Then the Lagrange multiplier, the value would be fixed by requiring that x dh was equal to w, right?
Sorry.
So x dot
Yes,
dh
precisely. Yes.
is equal to w. So if we didn't have mu, w would be fixed.
So that is effectively true, but in practice, when you use a Lagrange multiplier in this way, you you don't fix it a priori. You keep it as an integration variable, which becomes fixed at the saddle point effectively to the value that the dot product of x to dh would be fixed at the saddle point.
Right. So that's why okay. Again, I can delay this to the end, but as I said, I think that in order to get that delta function of x dot x equals n, you have to integrate over w.
Sorry, the delta function of x. Oh, this here?
The delta.
No, because this is again, right? This is, think about this schematically. This is going to be so if I have some super derivative, which is given by the derivative of respect to x, the normal one I use all the time, and the derivative with respect to omega, this is just the problem of doing the cat's rice for the normal cat's rice without Lagrange multipliers for the system that I'm taking the kind of the super derivative of h in the delta function. So this is just, I mean, these two delta functions here come from the fact that I need to include in the description of the gradient in the Lagrangian system also gradients with respect to the omegas.
Okay.
They are
let's delay it till
exactly
the
on
end.
the same level as
Okay.
the x's in this
Okay,
picture.
fine. I'm happy. Let's delay it till the end.
Okay. I mean, the Lagrange multiplier description and the immediately fixing a subtraction of the projection on the perpendicular, these are like orthogonal methods which produce the same answer. So in spirit, perhaps, but in practice, you keep it alive for a while until you have something which fixes it. So now we want to evaluate using these insights. You want to evaluate, and these shifts, right, are of mu. We want to evaluate our absolute value of the determinant. So we have the determinant of the Hessian, which is going to be the double derivative of h plus, I'll just immediately start calling it mu I, averaged, which we can write schematically for a given instantation of this double derivative of h, right? This is equal to the product over all of the eigenvalues of this matrix plus mu, absolute valued. That's the definition of the determinant, averaged over disorder, which is the same as e to the sum over all of the eigenvalues of the log of the absolute value of the eigenvalues plus the mu. Once again, whole thing averaged. Now this is getting to a form we like. It's a sum over the eigenvalues, which we're going to want to turn into an integral over the spectral density. Now it's in on exponential, which is going to make that step seem a little fishy, but the GOE has very nice properties. It concentrates extremely quickly on its properties as n gets large. And so in fact, we are justified in replacing in the exponential this with 1 over n, sorry, not 1 over n. That's very important. N over 1 multiplied by the integral over the spectral density of, the integral over the spectral density, the probability of finding a given eigenvalue independently of the rest, times the logarithm of the absolute value of the eigenvalue plus mu. And this will give us, way at the bottom of the board, e to the nth power times some function of mu. Right? The contribution from the Hessian in this picture, we fixed mu, is that in our big integral, we have a nice constant factor, which doesn't depend on any of other variables. It just depends on what we fixed mu to be. And this is an integral you can do. You can ask Mathematica, even with the absolute value sign, it's happy. And you might have to give it a bunch of assumptions about mu and stuff, but in the end, it will give you this function which involves square roots and things. It's nice. Yeah, Mathematica can do it. Again, you have to teach it a little bit with assumptions. Yeah, classic Mathematica, but it works. So this is some function. It's not that interesting to see, but it's some function that exactly gives you the contribution from this determinant. So now we want to deal with everything else. Removing this useful little term, unfortunately. So everything else is now that we've lost a couple things, we have this spherical constraint, we have the gradient being 0, and we have the energy is fixed to a certain value. The energy density is fixed to a certain value. So what we're going to do, I'm not going to go through every step of this because it would be a lot of writing and not that interesting, but the basic thing is to convert the delta functions into exponentials with the Fourier transform. So we go from the delta function of the derivative of h, the evaluated xa, plus mu of xa, equals an integral over an auxiliary field. I always put hats on my auxiliary fields. Divided by, okay, there's some normalization for the Fourier, times an exponential integral of I x hat transposed dotted into this gradient. Also, wait, there's an A here. These all have A's too. There's one for each replica. That's important. Not omega anymore, it's mu x A. So that's something we can do. We can make the same game with the energy, which for evocative reasons, I write as the auxiliary variable will be beta hat. No reason for now. Divided by 2 pi, e to the beta hat times n energy density minus HA. And these should have A's too. The A's and the beta hats are conceptually less important. Eventually, when we take replica symmetry breaking as our idea for what the order should be like, vectors of replicas will end up not having any sort of breaking. So they'll have one value in the saddle point. But in principle, there's one per constraint. So with this integral, and okay, do the same thing here. It's not very interesting. It basically is just going to fix something we could fix by hand at the end. But having done this, we now see something nice. Well, now we have an integral over a whole bunch of fields, 2 little n and some scalar fields left over, of exponentials that have a bunch of our fields in them, but which are linear in the HAs. And this is very nice because I'm going to save that board and go back to the Hessian and remove it. It's very nice because, you know, when you do Gaussian integrals, there's 2 kinds of Gaussian integrals we know how to do. There's Gaussian integrals that just you integrate over the Gaussian, and there's Gaussian integrals where you integrate over the Gaussian times the exponential something linear. Anything else becomes tricky. But this time we just have exponential linear things. We can use a nice identity in Gaussian integration, which is that if we have e to the, I'm going to say a sum over a, to be evocative, of some linear operator, so derivatives, multiplication, you know, linear operator stuff, hitting our function of xa, and I want to average this, I will get, because these are Gaussian, e to the 1/2, the sum over the linear operator, twice. This should be evocative from Gaussian integration of, what a shame, I have to erase that, of the covariance of the Gaussian distributed object, which of course is the defining feature of our model, is the covariance of this object. And so this will simply give us these linear operators, which remember include derivatives and things. So this will give us, you know, f primes and stuff in our final saddle point. This will give us an n over here, which is like what we like to see when we start to make saddle point calculations, on an n in front every time, by our beautiful covariance function defining our model, evaluated at the inner product between, now we've mixed the replicas. Replicas at 2 different A's and B's because of this Gaussian integration. So I'm not going to write the whole thing out. There was a slide in my talk on Monday which included it. It's not very insightful to see the form of this thing. The important aspect is that you find, having done this, again, you can teach Mathematica to do it. It's not so, you can also do it by hand in like 20 minutes. Is that it depends only on 3 different kinds of scalar products of our order parameters. You have x, A, transpose, x, B. You have x, A, transpose, x, B, hat, our auxiliary variables we introduced. And we have x, A, hat, transpose, x, B, hat. And these are the only things which enter the expression. And so it's natural to define them as order parameters that we will then, move out of the world of x's and x hats and into the world of order parameters, which is what we would like to do in the mean field calculation. So we can define a CAB, which is going to be this normalized by n. This is very much like the QAB in the normal replica theory. This is the overlap, how the inner product between 2 vectors, the very physical interpretation. I really didn't write these far enough away. This is going to be RAB. I'm stealing this notation from dynamics, where those who know, there's very close rhymes between this procedure and dynamics, doing dynamical mean field theory. Divided by n, and for nice notation purposes, I put a minus I here, but you can do what you like. It just changes the value that you evaluate. I want positive at the ground state. And finally, I did it again, a DAB, capital D matrix.
So everything is real here. Why do you have a factor of I?
Sorry?
Why is there a factor of I? Everything is real here.
It's a factor of I. Not everything is real. When I introduced our beautiful auxiliary variables, I added an I. And
so that's analytical.
You don't have to. If you don't have the I, you'll get something else for the expression of the saddle points as a function of an R prime or an R tilde. And you'll just evaluate different numbers. In the paper we wrote with Jorge and I, the I was nice because it meant, again, that all 3 of these matrices are positive at the ground state. And it's a nicer notation in the end. But it's really conceptually not very important.
Okay.
So I'm not from this field, but
Yes.
you mentioned order parameters.
Yes.
So these are order parameters of the ON symmetry of the model of what are you breaking? What is the symmetry that you're breaking?
Yeah, I'll talk in that a little more in depth in a second. So at the moment, we are noticing that our saddle point is a function of these scalar products, and we're trying to simplify the discussion by moving to an integral instead of over the x's over the scalar products instead. And so these are, literally matrices. These are, maybe after the end of the talk, if there's a time, I can describe the interpretation of these, which are kind of related to responses in a sense. This has a simple interpretation. It's saying I have 2 stationary points in the same random landscape, and I have a matrix of them, that's little n by little n, and I have the inner products of the stationary points that have been drawn from the random landscape in little pairs. What do their inner products look like? That's what literally this is. And I'll talk about how order in this model corresponds with structure of this order parameter in a second, after I finish the... I have to promise you a determinant of the Jacobian of this order parameter, in fact. So speaking of that, in order to make this transformation, we have to pay a little price, as we always do when we transform variables. We need a determinant of Jacobian, which has a schematic form, or symbol form. The product over all our dx's and our dx hats. In fact, even absorbing our 2 pi's, which we might have been careful to include because they're order n, but actually they just get wiped away by this transformation, ends up being the integral over the matrices, the n by n matrices, dc, dr, dd, times the determinant of the Jacobian, given by just the matrix C, R, IR transpose D. Where here the absolute value is not so important because this has some nice positivity properties. But this is our determinant of our, oh, sorry, one more piece. To the n over 2th power, because these are dimension n. Oh, sorry, to n over 2 power. And this also incorporates cleanly into our schematic of trying to get to a saddle point, which is that we can just exponentiate the determinant and have an e to the n over 2, n out front, always nice, of the logarithm of the determinant of the same matrix. So with this piece here I didn't write out, but which also has an n out front and depends on these nice order parameters, and in the order parameters constant piece contributed by the Hessian term, we have now something which is ripe for trying to take a saddle point. This is always very confusing because I'm talking about saddle points in the configuration space, and now I want to take a saddle point to evaluate an integral at large n, different saddle points, but this is a saddle point in the space of order parameter fields of all this stuff I've done, right? So effectively what we have now is that our complexity is going to be equal to the stuff that I've thrown away a while ago, 1 over n, the limit of n to 0, the derivative with respect to little n, of something I can write schematically as the integral over my order parameters, dc, dr, dd, d beta hat. First, I drop the a's. As I told you, it's not so interesting to keep them for now, but you could keep them. You'll just find they're all the same. I'm missing anyone? No. You could have an order parameter for the delta function keeping the spherical constraint, but all that's going to do is make the diagonal of C 1. So we just say the diagonal of C is 1, we have enforced the spherical constraint at the level of these ordered parameters. Of E to big N, we like little n times some effective action, I'll call it the Katz-Rice effective action, of all of our order parameters. So this is an integral with a big N in front of something that we're going to take n very large in front of some function of a bunch of integrands, or sorry, a bunch of integration variables. And so we expect to be able to evaluate this complexity as, well, so the complexity, so ignoring this part here with the ends, all this replica machinery, if you're just looking at this, we would want extrema of this action. And the value of the result of this integral would be e to the big N, little n, times this thing evaluated the extremum. And what happens after that? We take the derivatives with the little n, which brings down one copy of S and one copy of big N, and then we drive little n to 0, which kills the exponential, puts to 1. So in fact, the result of all this will be the action that I wrote, the Katz-Rice action, evaluated in all these order parameters, which are a mess, where I've kind of made a little fib here because these are n by n matrices, and I've taken the limit of n to 0, but I'll describe what is packed in this information in that limit in a second. Evaluated at an extremum. So this, now we've reduced the problem to the problem of finding a saddle point. Now what do we expect the structure of this saddle point to look like? This, yeah. Okay. Yeah, what time is it? Ooh.
Eduardo, do you have any questions before you leave?
No, well, I asked too many, and I guess it's better if I just leave.
Okay, so
Then
we'll record anyways. You can ask questions after.
So I can catch up later by recording. Okay, bye.
Thanks, Eduardo. Bye-bye.
Yeah, we can do some ADR where I just you can take my mouth from an earlier part of the talk and I'll record something and you'll make a little video where it looks like I'm answering the question, like they do to add jokes into movies. All right. So what do we expect the form of these order parameters to look like? Okay, let's go back to my sphere. So I'm not going to talk in depth about the interpretation of R and D because it's a little technical, but if after at the end we can maybe discuss it. C, though, is very interpretable because it's this inner product between vectors in the configuration space. And these vectors should be describing stationary points. So the question is, how do we expect stationary points to be distributed relative to each other in our problem? You can get rid of this too. Okay, so if I imagine I have a stationary point, and I choose a coordinate system for my 3D projection that has that stationary point pointing straight up. Now, we already know, right, that C of I, let's say I'm using A's. A, for any A, has to be 1. That's the spherical constraint. So if I write this matrix down, we can already knock out one piece of the matrix. The diagonal is all 1s. That's the spherical constraint satisfied. Now, if you imagine, let's say the simplest possible scenario, that would be the stationary points, knowing about the direction of one teaches you nothing about the direction of the others. This is they're totally uncorrelated. In high dimensions, almost all of the volume of the sphere in a given little projection like this exists on the equator. Vanishingly small as anywhere else. And so in this scenario, where the stationary points are effectively uncorrelated, with overwhelming probability, if I picked 2 from the distribution of stationary points, they would be exactly orthogonal to each other. And so we expect, okay, not all stationary points will have correlations. Those which have no correlations are going to have a contribution of 0, orthogonal, effectively. But this obviously is not the only possibility. In fact, it's very intuitive that there should be correlations between stationary points. For instance, if you imagine in your landscape, okay, the picture where there's no correlation means that every low-lying point, you're not any more likely to find another nearby low-lying point. So you have these weird, isolated low-lying points that have no nearby structure. This is a type of landscape, okay? But really intuitively, you imagine that if you have a low-lying point, it's because it's at the bottom of some canyon or something. And if you have a little canyon, maybe there's some structure down there, now you have some chance of finding nearby low-lying points, right? It's knowing that one exists means that there probably are some nearby. And so in some region that's basically the size of the canyon, you expect to find also, in a way that's not representative of randomly correlated points, stationary points with the same properties nearby, perhaps in some regimes of parameter space. And this gives us another typical value of the distance between the points. But remember, this isn't distance, this is overlap. This is the dot product. So this typical distance, the scale of the size of the canyon bottom, you can call it 1 minus the typical overlap. I'm going to call it C1. And if you imagine that I sort this matrix C by whether or not A, so CA is 1, CAB is 0 for AB uncorrelated. And CAB can be other things. It can be, for instance, something like C1 if AB are in the same canyon. Now, if you imagine I sorted this matrix, the rows and columns, by membership in canyon, right? So this vector down here also probably belongs to some canyon. And all these other orthogonal vectors, whose mutual overlap with different vectors in different canyons tends to be 0, they each have their own canyon they are part of. So if you sort the rows and columns by membership in canyon, you will find, okay, there'll be a block. All the members of this canyon will have a typical distance from each other, represented by the overlap C1. No overlap with the second canyon, but within the second canyon is the same picture. And so on down the line. This is this Parisi block structure, which is so famous. It comes from this geometric structure of solutions to the problem. But of course, you don't necessarily have only one kind of canyon, right? It's possible that inside this canyon, there are little sub-canyons where there's multiple points at the bottom of them. And that would lead to, okay, now a division into sub-canyons where an even smaller distance characterizes the typical range between points, which would imply some other block structure inside this block structure, having also agreed to sort the matrix into sub-canyons.
Sorry, John. I think I'm a little bit confused now.
Yeah, sorry. This is a very difficult thing.
Because these matrices now, they look infinite dimensional, very huge, with lots of structure, lots of place to put all these correlations.
Yes, yes.
But these matrices were 2 by 2, 3 by 3, 4 by 4.
They're n by n for a number we will take to 0.
Right, so they're not very big, and yet they have all this inner structure. How should I think about it?
This is a question that has dogged people for a long time. First thing to say is that it may seem like bringing n to 0 reduces the amount of space you have to work in. In fact, one of the early results of Giorgio Parisi was to show that the group of symmetries of matrices of this form in the limit of n to 0 is an infinite dimensional group, which is very strange and a very unintuitive result, which probably doesn't help your confusion, but it does indicate that this limit is strange and still gives you a very broad place to work in. The way that, I guess, intuitively you would think about this is to stick at finite n. And imagine that you have a very large but finite n, and you're pulling these vectors, n of these vectors in pairs, and you're asking, how should I expect them to be correlated? But you don't get the real answer till the limit of n to 0.
I imagine that I have like 1,000,000 replicas, and then 100 turned out to be in some canyon, the other 100 in another canyon, and so on, and that's how I grouped this million by million matrix.
That's how you would defend picking a certain structure for this matrix, right? But in the end, the saddle point, all of the evaluation of these order parameters like these C's will come down to taking the n to 0 limit. I don't know if I have a very good simple intuition for this structure, except in to say that it is quite complicated and preserves a lot of degrees of freedom despite this strange limit, which seems like it should destroy the degrees of freedom.
Let me ask another question about intuition. That one is probably simpler. At some point before, you used the fact that the second derivative was basically a Gaussian matrix, right? And therefore, you could do some simplifications of that determinant.
Indeed.
So, and you referred to some recent result by some mathematicians to show that. But can we argue for that factorization physically by just saying that we are dealing with matrix, vectors, and scalars, and there are many more matrix elements, and therefore, statistically, I should immediately be able to do that? Or what is the intuition?
You could try, but the point is that it's not true if you make a small change to this model, for instance. Like if you take the square of h instead of h as your energy. And so it really is specific to Gaussian fields. I don't know if I have a good specific intuition off the top of my head on this. I'm sorry. But it's only applicable to Gaussian fields. It fails completely, that division, if you move to even the simplest non-Gaussian fields. Again, still Gaussian disorder that just enters the exponential non-linearly.
Okay. Because it seems to me like everything is super clear, but then it depends on these super non-trivial steps. This one and that one, right?
Yeah,
so
it's true.
Not
Well, I'm going
totally
to touch on that first step
Okay.
later. This step is very non-trivial. It's also, I mean, in Rome, they teach a whole semester course on this method. So, like, it's difficult for me to kind of give you maybe a nice, careful intuition in this this short Blackboard talk I have.
Sure, okay, that's fine. Thank you.
Another curiosity here, it looks that you are looking for you are describing a sort of self-similarity property. So
Yeah, exactly.
do you have any characterization of these matrices in terms of some fractal dimension or multifractal dimension, something like that?
The matrices are not characterized by this sort of thing. I mean, they're characterized by 2 numbers per level. This number that characterizes the sort of size of the basin, the typical overlap of things that come from the same basin, and also a second number, which is so-called Parisi parameter, which is just basically the size of the blocks right? X1, X2. Now, the landscapes that are described by these can have interesting fractal properties. Like, for instance, in the case that was originally studied by Giorgio Parisi to solve the Sharon-Tinker-Patrick model of Ising spins, the necessary, so in that model, so just jumping ahead also in this problem a little bit, making this sort of ansatz for the structure of this matrix, and let's say the same structure for the other matrices, though of course with different values populating them, we're still left with a problem, which is how many levels of symmetry breaking to choose. And this, okay, you have to take your model, you have to evaluate this thing, you have to see if it gives you, if you're using a free energy, for instance, you have an extremal property, so you have to keep adding levels until you find that there's no more unstable directions, this sort of analysis. And in the Sharon-Tinker-Patrick model, it ended up being the case that you need asymptotically, another very strange result, an infinite hierarchy of levels, continuous hierarchy of levels of this matrix. And there, in fact, you have interesting fractal properties of the level sets of the function. But in the end, when you have a finite level, I mean, the canyons aren't really fractal because you have, basically, if you kind of coarsen your view of the landscape to the level of a certain type of canyon, you see that golf course I drew earlier where you have completely uncorrelated holes. And if you zoom in a little bit to the bottom, but you coarsen to the level of the next canyon, you'll see the same structure. So there's a self-similarity, but it's at each level, it's kind of a trivial one, unless you go to this continuous case, in which case you have a little more structure. So,
excuse me, Jaron.
Yes.
I just want to mention that I have to go.
Yeah, okay,
now I have to go. So it's just to say that. Okay. No, that's okay. Very good. See you. Thank you.
Okay. So we're getting close to the end here. Don't worry. So this is a way to take these matrix order parameters and give them some sort of meaning in the n-to-0 limits, right? If you populate this matrix with certain x's and c's, you take a saddle point at finite n, you continue those saddle point values. Hopefully it's the right saddle point for the n-to-0 limit. You go to n-0, you now have, okay, your effective action is a function of a bunch of, as many c's as you have canyon types, as many r's as you have canyon types, as many d's as you have canyon types, evaluated an extremum of the function you get by taking the limit carefully. Now this is not a very easy problem to solve for two reasons. First, the obvious reason, we have a lot of order parameters. A lot. And not just a lot of order parameters, but we don't even know how many levels to make a priori from a given f. The second thing which makes it even worse is that this is not, so when you do this kind of problem, usually in equilibrium, you have an extremal problem, right? The thing you started with, which wasn't this horrible thing, it was the sum of exponentials of real numbers, which is positive. So you say, mean field, your mean field free energy is going to bound. There's a variational bounds on the true free energy, which means that when you want to solve for saddle points of the effective integral, you can usually use minimization or maximization, which are quite stable relative to saddle finding algorithms. Here we have no variational principle at all, right? This integral is built out of delta functions. It's quite horrible, right? Our effective parameters were these Fourier ghost fields. And so if you put this thing into a Mathematica-find root and you initialize the values of your order parameters, you will, with very high probability, not find a good saddle point. You'll race off to infinity or minus infinity in a situation that gets increasingly worse as you add levels to the symmetry breaking. And so really, in order to describe this numerically, to actually get a number, how much stuff do we find at a certain level, you need to find a starting point, a seed to your problem. And there's two steps to find this seed. So the first step is going to be to return to Fadeev-Popov and continue that thought further. Right? In the Fadeev-Popov gauge fixing scenario, a very important conceptual thing to make sure the whole system works is based on the so-called BRST supersymmetry, which when you drop these absolute value signs, promote everything to ghost fields from the delta function, ghost fields from fermions that make the determinant into an exponential. You want to make sure that your physical values don't depend on ghost-related things. And this comes out of a symmetry, a supersymmetry that exists among the ghosts and the original fields. And in fact, we also have this supersymmetry in this model. All the time, actually. The determinant is not, the absolute value signs are perfectly fine. The origin of this symmetry can be easily seen when we look at this form for the count, which is that there is an exact symmetry of the measure related to shifting the gradient by a constant vector. Right? If you shift the gradient by a constant measure, a constant vector, you still get 1 every time. And we can take this symmetry and we can map it through our inverse function, in the neighborhood around a stationary point, and find a similar exact symmetry of this integral, which is a little nastier. It looks like taking the value of the field, the location of the stationary points, and bringing them to the inverse of the Hessian, bringing them to x plus the inverse of the Hessian, hitting whatever vector we perturbed with. Ooh, I'm right at the end. I shouldn't have done that. So this is what comes of this trivial symmetry of the first integral. You get some sort of very non-trivial, hard to work with symmetry of the second integral. In the scenario where we drop the absolute value signs, pretend we just do it, we forget all the consequences. This second uglier symmetry, which I should have written further this way, takes a more beautiful schematic form. So, imagine you drop these absolute value signs, you take this determinant, and you use n-dimensional Grassmann variables, eta and eta bar, to write the determinant as the Grassmann integral of eta bar transpose the Hessian eta. This gives you the determinant with the cost of some fermionic ghost fields. When you make this description, when you insert this into the problem, which is only valid when we drop the absolute value signs, this symmetry can be written instead, for schematic reasons related to the fact that you can only have 2 fermions present in any product of many fermions, as x plus eta bar eta transpose delta V. Now this can be worked with. If you're in a theory where this is your symmetry, now, if we consider eta transpose delta V as a single dimensional Grassmann perturbation, this is a linear symmetry. So this is the basis of the BRST. You start with this linear symmetry, you go into your effective theory where things have been promoted to exponentials. You see that when you apply this symmetry, you can indeed reabsorb all the delta epsilons into your other fields by transforming them with the usual BRST rules. And this gives you the BRST symmetries that are so useful. But they only work, again, when we can drop the absolute value signs. And I said earlier in answer to a question that we are okay to drop the absolute value signs when we know that the exponential majority of the points we're counting are minima or maxima. Because then we have a coherent sum. Maybe there's some incoherent pieces because there's some minority saddle points, but they're so much smaller by an exponential amount than the majority that the answer we get is correct. So an example of a place that we understand we can do this is the ground state. Because the ground state had better be mostly minima. Because if it wasn't, then you wouldn't have a ground state. You'd have downward directions. And so our ability to fix a certain place where we know the solution will be at the ground state. And the way that we will get all our order parameters, despite the fact it's very hard to do the variational problem here, not a variational problem, the extremal problem here, is by making a mapping with equilibrium, which also describes the ground state in a certain way when you take the zero temperature limit. And this will give us a very nice correspondence. So first, when this is valid, when this supersymmetry is valid, we have ward identities. So when we have supersymmetry, no, usually it's Susie, right? SS, come on, that's stupid. Susie, when you have supersymmetry, we have ward identities. And the ward identities, again, maybe a 10-minute exercise on the board. I'm not going to go through it right now because we have not so much time. Tell you that we have a relationship between our matrix order parameters. You find the ward identity implies that R, sorry, I should start with D. D is equal to beta hat R. Proportional by this scalar order parameter. So that's nice. We've gotten rid of 1/3 of our matrix order parameters by the ward identity when it's valid. Now, in fact, it's even better than this. Because this is a little bit of a detailed thing, but if you take the saddle point conditions for this problem, and you insert this ward identity, you find something more helpful, which is that the saddle point equations, given this identity, are only self-consistent if, in fact, R is further diagonal. This is kind of specific to this problem in a sense, because it came from the saddle point conditions we got for the effective action of this problem. This second, the ward identity is generic. This is not generic. This came out of our spherical problem. But this is very, very nice for us, because it means now, if we're looking at the supersymmetric effective action, we have one matrix order parameter, one scalar RD, the diagonal element of R, and our beta hat, right? Much reduced space. And with this reduction, we are now ready to make the mapping to equilibrium, which has a schematic form that should be somewhat intuitive, which is that so we know the free energy is given by, let's say the ground state energy is given by the limit of beta to infinity of the free energy of beta. And this, if we take our model here and we write down a Boltzmann distribution, we go through many of the same steps, a little simpler actually, because there's no delta functions to raise into exponentials. We get, likewise, that this should be the minus, let's see, let's divide this by n, this is the ground state energy density. I always want to work with energy densities. So it's a 1 over n here. So it's going to be 1 over n times minus 1 over beta to go from free energy to partition function times some effective action of equilibrium evaluated of a single matrix Q, the so-called overlap matrix, the more typical notation, evaluated at an extremum. Where, of course, there's a limit to 0 of the size of this matrix as well. And this should give us the ground state energy. We should also get the ground state energy by saying that the complexity of the ground state energy, where we've optimized over mu. So if we take the value of mu, which is most common at each energy level, right? The ground state energy should be the place where the optimized over mu complexity is 0. Simple enough. That's where we stop finding states. Or the highest energy, too. That's also true for this. So it turns out that there's two different ways to write down the ground state energy. But the correspondence is more than just schematic. There is a correspondence directly between the value of this overlap matrix in the equilibrium problem, it's the order parameters it contains, and the order parameters of the supersymmetric effective action. Very schematically, right? As you approach 0 temperature, your Boltzmann distribution concentrates among low-lying states. And it does so, if this is a stationary point, the overlap of a stationary point itself is always 1. But the overlap of Boltzmann distributed states at some finite temperature, finite below temperature, near a given stationary point, it has some small width, which is going to be 1 minus qk, the kth level of canyon structure of this matrix in equilibrium. But as beta goes to infinity, this is going to vanish. They're going to concentrate on the stationary point. And this affects the parameters of the order the x's and the q's of the order parameter matrix, where qk, this small width due to the thermal noise, goes to 0 like 1, or goes to 1, sorry, full overlap, like 1 minus some parameter y over beta, asymptotically to 0 as beta gets large. And also this width of the block, this is a little bit fast, I'm sorry, I'll finish up in a second. goes to 0 by some parameter z over beta. Yes? Yeah. So it's not non-degenerate. It's that there are a number of stationary points whose the number is less than e to the n. If there are order n stationary points, the complexity is 0. If there are order n squared stationary points, the complexity is 0, right? Because complexity is the log of the number for large n divided by n. So the only way for this thing to be greater than 0 is if there are e to the n times something stationary points. If there are n squared, it's 0. If there are n to the 60th, it's 0. So there can be a lot. It can be degenerate. It is true, though. There are examples in machine learning, right, where you have, when you're in the easy phase of a problem, it means you easily find solutions. When you're in the easy phase of the problem, you have like, you no longer have this property where the ground state is, the ground state has isolated stationary points, because now in the easy phase of a problem, you've over-parameterized so much, say, that you now have little manifolds at the low energy states of solutions. So a lot of this goes out the window. So there are cases where you have an extensive number of stationary points, extensive complexity, excuse me, at the ground state, but it's not true here.
So what does it mean physically, sigma equals 0?
It means that, right, so sigma, remember, is 1 over n, the log of the number averaged. So that's saying that in the large n limit, this beats this, basically. It beats the log. So it's the only way to beat the only way for the log to beat the 1 over n is to have an exponential inside the log in n.
So this is valid only in the large n limit.
Yes. Everything I'm working on here is when we're taking saddle points with respect to a variational action with large n.
Okay.
In practice, you start to resolve these things order thousands or 10,000s. I have friends who've studied DMFT solutions which rely on the same assumptions on these models and compared them with simulations, and they start to resolve things like threshold energies, like I described in my talk, around thousands, tens of thousands. So the schematic correspondence happens to be that in the limit of beta to infinity, you get that y from equilibrium equals RD from the complexity problem, z from equilibrium equals beta hat from our complexity problem, and the limit of the Q matrix has a correspondence. For instance, the Q 1s, 2s, 3s, whatever, except for K, which has vanished, approach asymptotically the C's, 1, 2s, 3s, whatever, from the complexity problem. So this is nice, because again, equilibrium is a variational problem. Equilibrium has lots of attention and theorems about how to find how many levels of braking you should include in order to decide that you're done. So in equilibrium, you can do a lot of work to find out about the nature of the ground state, exactly what order parameters you should be using. Finish that work in equilibrium, take the results, and steal them away to your complexity problem, where you can plug them in and have a valid saddle point for the ground state. And then you can continue that result to the rest of the space. That was what I was describing in my talk on Monday. So that's that result. That's the end of this discussion. And I have a very short discussion of beyond Gaussian fields, basically just highlighting the problems that arise when you try to do that step. Is that okay? Can I go for 5 more minutes in this sense? Okay, sure.
Which I delayed until the end, but...
So I prepared 50 minutes of continuously spoken time.
The question is, I don't see any supersymmetry. What? I guess you use the word supersymmetry, but what do you mean by supersymmetry?
There's a mixture of
supersymmetry?
There's an exact symmetry of an action that contains scalar fields and Grassmann fields, which mixes the scalar and Grassmann fields.
What's the transformation that mixes them?
It's literally, if you go to Jean Justin quantum field theory book, it's literally the BRST transformation.
No, but I know what the BRST symmetry is, but can you just tell me? So supersymmetry is not BRST symmetry. Supersymmetry is symmetry that...
Well, BRST symmetry is a supersymmetry.
So, at least in the literature that I'm familiar with, it's a fermionic symmetry. Its square is 0 BRST symmetry.
Indeed, yes.
Supersymmetry
It's
normally
true,
is not
it's
a
true,
fermionic
it's true.
symmetry whose square is 0. But in any case, that's just language. But I just want to see what's the transformation?
Yeah, I can absolutely write down the transformation. I have some extra notes for this purpose. So we have our fields x hat, and we have these Grassmann fields that came out of promoting the determinant. And the transformation is, thank you, is some operator, which I've now reused curly d, but it's traditionally in BRST curly d, which is given by eta bar by the differential with respect to x plus x hat by the differential with respect to eta minus beta hat eta bar, the differential with respect to x hat. This is the symmetry. So you apply this to the action that you get when you take this equation here, replace the determinant with this Grassmann thing, and replace the delta function of the Hessian with the exponential form I spoke about with the x hats. And this is the differential symmetry for small changes to the values that you get. Yeah, so the shifts, the little shifts you get are that x goes to x plus eta times eta bar, times a small fermionic perturbation. X hat goes to x hat plus minus beta hat times eta bar times a small fermionic transformation.
Symmetry. So I'm just trying to understand what the original symmetry was.
It's unrelated to the fact that it's a gauge that you put in here. It's related strictly to the fact that we inserted a delta function. Every time you insert a delta function and you include a Jacobian, and you drop the absolute value signs, you have a BRST symmetry. It's kind of geometric in this sense. It's not actually related to the fact that the thing that we put here was a gauge fixing term.
Okay, let me think about it. I'll think. Okay, thanks. Any other questions?
I'm a bit. I mean, from your first talk, I was understanding that most of your work was on the non-pure case.
Exactly, yes.
Here, instead, everything is more in the pure case.
No, sorry. I might have misled you by giving you the example at the beginning of a specific f. But
see.
Everything here was in terms of f and its derivatives. So you insert whatever you want for f. You can insert an exponential function for f. As long as all of the coefficients of the Taylor expansion are positive, it's a valid covariance function. You can insert it, and all of this stuff just depends on f and its derivatives, evaluated at 1.
But so if you consider all, because as far as I understood from your first talk,
yes.
the case with the pure case was essentially solved, am I right?
Yes, yes. And
so
it's
in that case,
non-generic. In fact, what I did here was not valid for the pure case. Because and it's subtle, because in the pure case, fixing the energy for reasons related to the constraint and the homogeneity of the polynomial already fixes mu, effectively. So by inserting the energy and mu as delta functions, I've inserted the same delta function twice. And if you try to do this for the pure case, you find that you have singularities in the saddle points you try to take. So you want to not insert the delta function of mu in the pure case.
So put it differently, you cannot use the pure case as a sanity check for this machinery.
You can use it, but at an intermediate step, you have to make sure
you have
that
to modify.
You
so
don't
okay,
insert
so
that
I see.
Yeah.
I see.
Yeah. No, absolutely. You can use the pure case as a sanity check. It's just that the pure case has this very non-generic feature where those two delta functions, which for all purposes should be independent, in the pure case are not.
Okay. Okay, got it. And instead, let's say, historically, people that solved the pure case didn't use this this machinery. You built it. Let's say you and Jorge built it.
So a lot of this machinery existed before us.
I see.
We put a lot of pieces together.
I see.
In this field, the most common technique for finding this complexity did not use this machinery. This is something that recently mathematicians have tried to use more because they can make rigorous statements using these forms, not with the methods I've shown, but using the Katz-Rice form.
I see.
The way that most physicists have in the past computed these things is with a very nice trick.
Okay.
It's related. It comes from a paper by Rémy Monosson in 1995.
By?
Rémy Monosson
Okay.
in 1995, who showed that you can write down the complexity, the entropy of metastable states at any temperature by taking an equilibrium model, which is now not here, so I don't want to point at the board, an equilibrium model where you basically, like the replica method, take some power of the free energy, but rather than make the power something you bring to 0, you use the power as a parameter. And it turns out, for reasons that are kind of beautiful, but I don't have time to do the lesson on right now, you can get the complexity of metastable states, like the number of pure states, basically, in the Boltzmann distribution, by a Legendre transformation of the free energy as a function of this exponential parameter with respect to that parameter. It's a very nice thing, but it only gives you the dominant population. So it's like you've already optimized over mu. And so for a long time, people missed this thing that you have multiple coexisting exponential populations of saddles and minima and different kinds of minima, which has proven so important for understanding what we see in dynamics. For a long time, people said, it's like the pure case. We have this method, which is very easy for us to compute things, which only gives you the most common population, and it predicts something which is much like the pure case, right?
I see.
And it's only when we make the choice to fix higher derivatives like this trace of the Hessian, that we start to discover, okay, actually there's heterogeneity among the population of stationary points at given energies, and that appears out of equilibrium in dynamics as non-trivial behavior that you wouldn't guess from just the dominant population.
I see. Okay.
Yes.
So just for me to understand again, so your model only depends on this correlation of ages, so this f function.
Yes.
Now you found a formula for the complexity, or the log of the sum of the extrema points of this model. Okay, and that depends on C, R, D, beta at the extremum. But then you only have this function f. So what you're saying is that you can compute what this function C, R, D, beta are in terms of f?
At the ground state, you can. At other points, you have to use a numeric saddle point solution. So you have to, it's still valid at infinite n, but you say, okay, I have this very large system of equations that express the saddle point conditions that I can't solve as an explicit function of f. But of course, the results, which you then use Mathematica fine root, take little steps to your nearby a good solution, they do depend on f in a deterministic way.
Okay, so let's concentrate on the ground state.
Yes, yes.
So for the ground state, you can compute this complexity.
Yes. Well, it's 0 by definition, but
which is 0 by definition.
But you can compute the order parameters.
Right. Okay, so let's not concentrate on the ground state.
Well, so the point is, what is computing? And when I say numerically, I mean we are evaluating this saddle point exactly. Mathematic arbitrary precision, not with some finite n approximation, right? We have a system of equations. It's just too hard to, it has terms to the 5th power or something. You can't. We solved it in the sense that we reduce it to a set of equations that we can't actually solve because of the constraints of mathematical theorems, but we solve those equations to arbitrary numeric precision.
That's all right.
Yeah.
Okay, let's go to another ground state. Another state that has a non-zero complexity.
Yes, yes.
That you can compute using your method. And my question is, now suppose you do the simulations of this model in your computer, finite n, etc., just a large number of n, and then you compare with your method. Has this been done?
It's quite difficult to do simulations where you count stationary points. One, because there are exponentially many. So the task of counting them would become very difficult, just
Even
if you
you're
could
not,
find them.
even if you're not in a highly excited state.
But if you're at the ground state, you can't access the low-lying
ground
states.
state is 0, right?
No,
You
no,
said-
but if you're near the ground state, you can't access the low-lying states because there are spin glass or glass transitions which make dynamics very slow. Now, the types of predictions which do come from this that you can actually test. So if I change this problem a very slight bit, which doesn't actually change much of the analysis I did, and I add also an external field, a deterministic external field. I say, okay, I favor directions like this. This is an old result, but as you increase the strength of the field, the landscape with a strong enough field trivializes. The complexity becomes 0 everywhere. You go from having this horrible bumpy thing with very small fields, small signal to noise in a sense, to a trivial situation where it's very easy to find the direction of the field because there are no metastable states stopping you. And that, you can make the calculation, compute the place at which the strength of the field for which this prediction happens, and this agrees perfectly well. I mean, so counting the complexity itself, that direct prediction is not so helpful. But, for instance, as I said in my talk, the complexity of marginal states, these asymptotically flat minima, they seem to predict very well where algorithms like gradient descent or fancier algorithms like message passing, where they find solutions when you try to quench your model. And so there are ways to test these predictions, but they're not direct. You do not literally go and you count an exponential number of things with respect to the system size. This isn't really feasible.
Okay. And just to summarize, what are the assumptions made? One of them I remember is because of the absolute value that you need only a dominance of some
Yeah, the ground state. So
minima or
you
maxima.
to do the whole supersymmetric mapping, you need to be sure that the fact that you dropped these absolute value signs doesn't give you an incoherent sum. That you have almost all the points that you're summing up are contributing in the same sign.
Right. But that's the only approximation?
I mean, there's also large N.
Large N,
There's the
yes.
approximation that the answer is given by a replica symmetric form, which from
So this is-
50 years of
okay.
experience, it seems like a very good approximation for models like these, but
Okay.
it's nonetheless an approximation. The matrix could do whatever it wants in
It's an
principle.
assumption even, no?
Yeah. Assumption, sorry, an assumption. What else? I think that's about it. I mean, then a lot of steps, I was throwing out things which would become important if I wanted the 1/n corrections to this answer, to this value.
Okay.
Those weren't quite I mean, I justified throwing them away,
that's
but
fine.
I mean, this sort of thing also exists.
That's fine. Okay,
Yeah.
thank you.
Sorry, I just have a stupid question. So you want the determinant of Hess of H to always have the same sign, right?
If you want to throw out the absolute value signs, this has to be true or you'll get a bad answer.
Right, so that means all the eigenvalues have to be have to be an even number of -1 eigenvalues, right? Well, minus, what's the, sorry, you have to
Sorry.
have
If you're on a
even
maxima,
number of
then you
negative,
have... Yeah. Sorry. Continue.
sorry, I don't know how your definition of maximum minimum, but they all have to be, you're going to tell me that they all have to be the same sign, or they all have to be an even number of minus signs, or what?
So they all have to be the same sign because...
But let's say they're all negative.
Yeah, they're all negative.
Well, then it could either be an odd number of negatives or an even number of negatives.
That's true, but it's, in the practice, not actually very important because you could just
Okay.
redefine the problem. If you're searching for maxima, so all negative would be a maximum, all downward directions.
Okay, so
You could just take h to be minus h and pretend that that problem doesn't exist.
Okay.
Now, the reason, in principle, you could imagine trying to fix a specific index. Say, I have 30 negatives and 400 positives, and that in principle, that might work because they would sum constructively. But in practice, it fails using mean field methods because, again, our ability to fix the eigenvalue using the methods I showed is only good within order n. And so you have all I've done, I haven't fixed the eigenvalue, really. I fixed the matrix to, have a spectral density asymptotically which looks like this, right? And this means that when I say, okay, a typical example of the matrix will have an index, a number of negative eigenvalues given by making the integral up to 0 of the spectral density, but this is only something that I can be confident in the accuracy of up to order n. So at smaller orders, the corrections there are little variations between each stationary point back and forth, and this screws up, right? If I try to fix saddle points by fixing the spectral density, it screws up the sum by making the incoherence from small fluctuations about a fixed index.
Okay, I guess sorry, again, I'm not in the field, but
Sure,
I
sure.
would think they have to be all positive.
Yeah, they all have to be all positive or all negative. I mean,
Okay, so there's no some of them being negative. You have to have
no, so yeah, we can't do that. With these methods, you can't. People, I mean, there are ways to specify that you're counting, for instance, low numbers of index saddle points. You say, I want to count like saddle points with 1 downward direction or 2 downward directions. The way that you effectively do this is that you put yourself in a regime where you're counting minima, and then you use large deviation principles to say, well, I pull 1 eigenvalue out of the spectrum over this line, and I say, okay, that gives me a cost due to large deviation principles to pull an eigenvalue from the spectrum that's order e to the n, so it's comparable with the complexity. You do find exponentially many order 1 saddle points, index 1 saddle points, with an isolated eigenvalue, and a spectral density over here. But they are always, because this is a large deviation, they're always less numerous than the minima that have the spectral density associated with the large deviation you're doing. So this sort of thing can be argued, but this is only for this situation where you have a spectral density which is does not have a pseudo gap on 0, only has support in positive eigenvalues, and then you make large deviation arguments to pull out eigenvalues into negatives.
And maybe I should know this, but so how did you use the BRST symmetry? I missed.
The BRST symmetry allowed us, so I skipped over the details, but it results in a set of ward identities. In fact, you can get the ward identities pretty quickly from this, applying it to correlation
what
functions.
You mean just that the action has that symmetry? Is that what you mean by
the ward identities say that the order parameters evaluated at the saddle point has the symmetry. You say that 0, the symmetry applied to, for instance, I'm going to use abuse notation here, but imagine that the whole cat's rice mechanism is wrapped around these angle brackets. Applied to something like x transpose x hat has to be 0, right? This is the ward identity. It's saying that the symmetry applied to correlation functions, it has to vanish. But the correlation functions are invariant under applying the symmetry.
So D is a fermionic symmetry, right?
Yes.
So how can a fermionic symmetry on a bosonic correlation function be non-zero?
Well, you apply this. I mean, the dx applied to x will give you eta dot x.
Sorry, every fermionic correlation function is 0, right? You can't have a correlation function which is fermionic.
It's true. Yes.
So I think what you wrote down is identically 0. I don't think this.
Okay, so let me see really quickly. I can write down the real. Yeah, you get the word identities actually from looking at things which should be 0 anyway, and
So
applying the
if
symmetry.
that was
to them.
fermionic, yeah, that would
Like
make
this.
me happier. Okay,
This
that's
is
fair,
sorry.
that's
I made a mistake the first time. I was just making a schematic form. So
Okay.
you get all of this by doing this on that, and this on the other option, which is the x hat version, the x version of this thing.
Okay.
If you apply this to this and apply this to
I
this, you
understand.
get equations that you can then manipulate slightly to get this right out.
Oh, okay.
Yeah.
Okay, thank you.
So we were able to simplify dramatically the form, which corresponds with the mapping to equilibrium by applying the ward identities from the supersymmetry,
Any
or
other
the
questions?
BRST symmetry, if you will.
Okay, thanks very much, Jaron.
Okay. Whew. Sorry about the length. You had a lot of questions, though. How long was it? 2 hours. 2 hours, I would say. We started a little late.